Welcome my friends. So and welcome to my next lecture. So now I think last couple of lectures I already discussed the notions of differentiability and existence of partial derivative, directional derivatives, in other words the differentiation and some applications I have talked about. Now I moved my discussions from differentiability to the notions of integrability. So, like in the single variable case, you know the notions of Riemann integrations. Okay. So, now the question is, can I have if I have a function instead of R to R, say R2 to R or say Rn to R. So, can I extend the notions of integrability in the context of scalar field? So, that means the differentiation part is over. Now, I move to the integration part. So, first object to talk about is the concept of double integral, and then associated Fubini's theorem will be there. I will talk about that, what do I mean by Fubini's theorem, and then as an applications you will have volume areas will be there. Then there is a notion of what is called change of variables in double integral. So, this is the kind of concepts I plan to discuss in this lecture. Okay. So, as I said, so I should start with a scalar field. That means I have a function, right, from some subset R, subset of Rn, that in dimensional Euclidean space, to real valued function, that is called scalar valued or scalar field. Okay. If I have a scalar field, now can I have the notion of what is called integrations? You will see the notions of Riemann integral that you know for functions from R to R or some closed interval a b to R. The notions of Riemann integral you can extend in the context of functions from Rn to R. So, for R2 to R it is known as double integral, for R3 to R it is known as triple integral, and then if you have Rn to R it is called multiple integration. So, let me start with very simple case. That means, if I have a functions from R2 to R, then how one can extend the notion of Riemann integral in the context of functions from R2 to R. So, as I said, so this is the learning outcome of this lecture. Okay. So, in next couple of lectures, so you will learn the notions of what is called Riemann-Darboux integrations or Riemann integrations of there are certain restrictions of a bounded scalar valued functions f defined on some subset R, subset of Rn to R over a simple bounded region. So, I will take my domain is very simple bounded region. I will have a bounded functions, then I will try to introduce the notions of what is called Riemann-Darboux integral. So, for n is equal to 2, that means, if I have a functions from R2 to R, that is known as double integral. Okay. So, double integral for functions f from some subset R, subset of R2 to R, that means real valued functions, where R is a rectangular region. That means, I will have a region something like that, very simple region. Okay. So, in this region, what will be the notion of double integral for this sort of functions? And then I will introduce the notions of iterated integrals, and then you will see Fubini's theorem somehow gives some connections with the iterated integral and double integral. Like, you know, if you kind of go back to the differentiation case and you see when I talked about the notions of limit of some functions like vector valued functions or scalar valued functions of vector variable, then you will see the notions of like double limit is there, then you will have concept of iterated limit, right. So, that means if I keep one variable fixed, then if I think about the function of single variable, then do one limit and then perform the limit in the other variable. So, there is a notions of double limit, there is a notions of iterated limit, and of course, there are a couple of examples, some sufficient criteria. I have discussed the existence of double limit, iterated limit when they are equal. So, those sort of concepts are there in the context of limits. Similarly, if I once I introduce the notions of integral, then you will see the notions of iterated integrals. That means, like the parallel kind of thing, that means you have to keep one variable fixed, think about as a function of single variable, and you know the notions of Riemann integral, and then do the perform the integral in the other variable. See, so if these things happen, then it is called iterated integral. And double integral, of course, you just directly you have to define a Riemann kind of integral in the context of functions from R to R. Then one can ask that is that in connections with double integral and iterated integral, and then you will see Fubini's theorem plays a crucial role to conclude about that. So now I will start with the definitions of double integral. That means I will have a functions f from some set, say if I start with very simple domain, say square subset of R2 to R, then how I can define the notions of Riemann-Darboux integral. So now what is Riemann integral? If you remember, if I have a function say from some closed interval AB subset of R to R, then you are aware that what is the definition of Riemann integral. So suppose this is my R real line, and suppose you have an interval a to b, and if you remember, you have to take a partition of your interval domain, you have to take a partitions, okay, and you can have a concept of Riemann sum, right. Suppose if I have a partition like say x naught is equal to a less than x1 up to less than xn is equal to b, this is my partition, and corresponding to this partition p, if I consider this Riemann sum of this my function f, which is nothing but sum over say j from 1 up to n. Okay. So then what you have to do, I think if this is your partition, if you remember, that means the length of the interval, that means xj minus 1, okay, that is length of the interval, and then value of the function at some point xi j, where xi j is a point lies xj minus 1 to xj. So if I have, so that means this is my, suppose this is the interval xj minus 1 to xj. Okay. So if this is my interval, take a point xi j, arbitrary point from the interval, take the value of the functions at xi j, then hit it by the length of the interval xj minus 1, take a sum, so it will give you say some number, and then what you have to do, you have to do the if partition norm. There is a concept of norm. So partitions norm means what? You just take the length of the interval, each sub interval, like xj minus 1, and take the supremum, that is called the norm of the partitions. Now if norm of the partition is goes to 0, that means if I take a finer and finer partitions, that means if I take more and more partitions of the interval, and suppose this limit exists, that means limit norm of p, that means norm of, I will talk about in the context of R2, what do I mean by the norm of the partitions, same concept will be extended in the context of R2 to R. So in the single variable case, if this is exists, say some point, say let it be say capital A, then I will say that yes, my Riemann integral exists, my function is Riemann integrable, and this is denoted as integration a to b f t dt. So that is for a single variable case, you know. So now the question is, instead of single variable, if I have a functions from say instead of closed interval a b, now I am in a subset of R2. So now instead of closed interval a b, you just have a R2, so you just take a square. So that means you have a, in the x variable you have a closed interval a b, and y variable you have a closed interval say c to d. So that means you consider this square. Okay. So now if I have a function defined on say a cross b, a to b cross c d, c to d to r, if I have that kind of functions, assume all the things, that function is nice. So then can I talk about integration over this domain, that means ab cross cd of f, can I extend the notions of Riemann integrations in this context as well? Answer is yes, you can do the similar sort of things what you have done in the context of single variable case. Single variable case, what you have done, you have an interval, you take the partitions, make a Riemann sum, and or this is one of the way. Another way, you have to make a upper sum, lower sum, and then upper integral, lower integral, and then there is notion of what is called integral of f. That is same as if I take the Riemann sum, and if Riemann sum, if this converges to some limit as norm of partition goes to 0, that will give you the Riemann integrability of your functions f in the context of single variable. Similarly, what I will do the parallel setup in the context of function defined on some square subset of R2 to R. What I will do now, this time I have a functions defined on R2, that means this kind of thing set. Okay. What I will do, instead of taking a partitions in AB, you have consider partition of AB as well as partition of CD. If I consider partition of AB as well as partition of CD, what will happen? So you will have a partition of your square R2. Okay. That is called a grid actually. So that means what you have to do, you have to just partition the way you have done in the single variable case, partition of the interval. Now you have to take a partitions of your square and take a small square and apply the same process. and small square you can write it as earlier it will what will have is just interval xj minus 1 to xj. Now you have a partition on x axis in the interval AB, you have a partitions on the y axis in the interval CD. So what will be the small square? So that means it is nothing but if I denote it as xj minus 1 to xj, then cross yj minus 1 to yj. So that is the small boxes like this kind of things. I will show you, I have a picture here. So in this, make a area of this small square, take any point, make a Riemann sum, and then give the similar sort of argument. As partition goes to 0, that means if I take a more and more finer partitions of your square, that means more and more finer kind of what is called this small boxes, if their area or what a diameter goes to 0, then whether the limit of this double sum, that means sum over I, sum over j, because you have a partitions over the square. So interval means only if I have only one indices I. Now you have a partitions over AB in x axis as well as CD in y axis, when double sum will come. So first x axis if I denote by the indices I or j, the second axis or y axis it should be either j. Okay, so that means I have double sum I and j. Now I will argue in the similar directions, like if norm of the partition goes to 0, whether this Riemann sum converges to some limit or not. If this the limit exists, then I will say that yes, my function is Riemann-Darboux integrable. So that means the same context you can extend in the case of functions defined on some nice domain, that is square a cross b, a to b cross c cross d to R. Okay. So that exactly I have written. So partitions or mesh or grid of a rectangular region. So partition of interval you know. So like this one. So if I have partition means if I have a partitions of AB, then we start with x naught is equal to a, x1 x2 up to xn is equal to, this is a partition. So that means you can partitions your interval, this is x naught, this is x1, this is x2, this is up to this is xn. So that partition of a interval in the x axis you know. Now you have to just repeat the same process, take a partitions in the x axis of the interval AB, take a partitions of the y axis in the interval CD and put together and make a partitions of your square and apply the same process. That's it. Okay, look, so that's exactly I have written. Okay, so partitions or mesh or grid, same in different book uses different kind of word for this partitions of this rectangular region. So it says that let R be a bounded rectangular region. You look at the statement, it's very careful. So I am starting with a bounded rectangular region. So that means collection of all those points x, y in R2, where x is standing over a to b and y is standing over c to d, where a is strictly less than b, c is strictly less than d. So that means what you have, so that means suppose this is my a, this is my b, this is my c, this is my d, then what will be my region? That means this is the region I am talking about. So this is the region I am talking about. Okay. Now consider the partition Px of AB. So now once I have a closed interval a to b, that is in the x axis, you will have a partition, right? You can take a partition, finally many points, whose first point x naught is a, last end point is xn is equal to b. Okay, so x naught is equal to a, xn is equal to b. Consider a partition py of cd, that means take a partition of this interval, okay, or here, fine, where y naught is equal to c and yn is equal to d. Okay, now you just combine. So that's exactly I have written. So p script p is nothing but px comma py. So px stands for partitions of the interval AB in the x axis, py stands for partition in the of the interval CD in the y axis. So this together forms a partitions R of how many sub intervals will be there. If x axis if I have a m partitions and y axis if I have a n partitions of the interval AB and CD together, then if I combine it, then it will have m times n, this m times n subrectangles or cell as follows. And what is that? That I exactly I have written. This is Rij. So that means it is a collection of all those points in R where x running between xi minus 1 to xi, that means this interval, and y running between yj minus 1 to yj. And this is actually if I denote it p as Rij, where I running from 1 up to m and j running from 1 up to n, this is called the partitions or mesh or grid of the rectangle R. Clear? So if I have a rectangle, of course it is of the form close interval AB cross close interval CD. What you have to do, you take a partitions of your interval A to B, okay, let it be indices by say I. So that means the first point x0 is equal to A, then you will have a second point x1, third point x2, so on so forth, and end point is xm, which is exactly equal to B. That is a partitions of your interval A to B. That is one partition that I denote it as Px. Then you take another partitions in the interval CD, which is in the y axis, and let it be indices by J. That means if I start with C, y naught is equal to C, then you will have a y1, y2 up to yn, which is D. Then you combine these two things, px comma py. That means you take a small interval, like I denote it as Rij. That means I stands for the interval xi minus 1 to xi, that exactly I have written, and j stand for the interval yj minus 1 to yj. You consider Rij, which is the collection of all those points xy where x lies in between xi minus 1 to xi and y running between yj minus 1 to yj. Then if this is my Rij, then if I denote P is the Rij where I running from 1 up to m corresponding to the partition of the interval AB, and j running from 1 up to n, which is nothing but the indices in the partitions for the interval CD in the y-axis. Then this together forms a partitions of your rectangle. That is called either partitions or mesh or grid. And I already explained in my pictures that in other words what I am doing, I have this, suppose this is my square. So, okay, this is my partition in the x-axis, okay, and this is my partition in the y-axis, okay. Then what I am doing, you just draw a line here, okay, corresponding to the partition in the y-axis, and then do corresponding to the partition in the x-axis. I am very bad in drawing, nevertheless this is the, so this is the small boxes, like this is the small boxes. This is actually, you can write it as xj minus 1 to xj cross y, or if it is I, so that means xi minus 1. So, this is, you can write it xi minus 1 to xi cross any yj minus 1 cross yj, comma. So, that means this is the corresponding ijth element. So, this is the partitions of your square A to B cross C cross D, and then you can just make, like in the single variable case, make upper sum, lower sum or Riemann sum, and conclude that yes, as long as the limit exist, if norm of the partition, I will explain what do I mean by norm in the case of R2. Same thing will happen, but here actually because norm means what? So, earlier you will have just length of the subintervals and take the supremum. Here also similar kind of things happen. Either you can talk about the norm of the partitions by area of this small rectangles, subrectangles, or you can have a notions of diameter, because anyway if the area goes to 0 of the each subinterval, that means norm of the partition goes to 0, or diameter goes to 0 means also norm of the partition goes to 0. In any case, you can choose anything. And then if you say that okay, if the norm of the partition goes to 0 and if the limit exists, then I will say that Riemann-Darboux integral or Riemann integral exists for these functions. Okay, as I said, the picture is given. For example, this is your square. So, this is the square of the domain. So, and what is the grid or mesh for this? So, like for example, this is the partition for the x-axis. Look, I have noted it down. So, this is x naught is equal to a, then x1, then you have x2 up to xi minus 1 xi, and then up to the end left right hand point xm is equal to b, and similarly you have a partition for in the y-axis. So, this is y0, this is y1, this is y2 up to this is yn is equal to d, and if I just have it, so this is the grid. For example, if I take this is the one, so this is actually, so what is this? This is actually see xi minus 1 to xi, and this is yj minus 1 to yj. So, this is actually the interval what is called xi minus 1 comma xi cross yj minus 1 to yj, and if you remember, this is I have denoted as Rij. So, this is the small subinterval after partitioning my full rectangle. In the x-axis, take a partition in the x-axis, take a partition in the y-axis of the interval AB and CD respectively, and then if you join it together, then it will be partitions of your rectangle whose one of the subinterval is Rij. So, I stands for the partition for the x-axis and j stands for the partition for the y-axis or of the interval CD, and I stands for partition of the interval ith subinterval of the partitions of the interval AB. Okay. I think it is clear in the picture. Okay. So, now look, so then I will define what is called mesh size, grid size or norm of a partition. So, what do I mean by norm of a partition? So, if I have a set S which is subset of n dimensional Euclidean space, then there is a notion of diameter. Okay. So, and that I denote it as either delta of S or modulus of S or DIM of S, which is nothing but supremum of norm of x minus y, because if I take x from S and y from S, S is subset of Rn, that means I have 2 points in Rn, then you just talk about the corresponding distance between 2 points in Rn, and what is that? This is the Euclidean distance or norm of between x minus y. Though I have written this is small, but actually this is norm of x minus y. So it's okay, it's completely clear, it's completely understood from the context that whenever I am talking about modulus of x minus y, and if xy coming from Rn, that means I want to talk about the distance between 2 points in Rn. So it is automatic that the distance between 2 points in Rn is nothing but norm of x minus y, even though I have noted it down by mod. It is well understood. Okay. So once I have the notions of diameter, the supremum, because I have a bounded set, I am starting with a bounded set, so therefore supremum will exist. Okay. So now at least for the rectangular case, okay, for this one we will see. So let R be a, now look, so this is diameter, means this I have defined. If I have a set, just take the supremum, then distance between any 2 points, and take the supremum of any two x varies over S, y varies over S, that is called the diameter. Now if I start with a bounded rectangular region, of course R, and what is bounded rectangular region? Even very specific bounded rectangular region I have taken. That means R is actually what, all those point x y is in R2, where x is running from A to B and y is running from C to D. Again, in last picture you have seen, this is kind of this kind of region. Either origin will be there or origin will be somewhere else, so it doesn't matter, or you can have this kind of things. Okay. So this is kind of R I am talking about, rectangular region. Okay. So now you take a partition P. What is your partition? It is the collection of all Rij. Rij is nothing but the small square inside this rectangle. So Rij, which is I is running from 1 up to n and j is running from 1 up to n. I just explained what do I mean by Rij, which is nothing but the cross product between the interval xi minus 1 to xi and yj minus 1 to yj, where x0, x1, x2, xn is a partition of your interval AB, and y0, y1, y2 up to yn is a partition of your interval CD. So if P is a mesh or grid of a rectangular region R, then the mesh size, grid size, or norm of the partitions, how I can define? I am saying this is the notations norm of P, and which is nothing but the supremum of diameter. Now Rij is a smaller rectangle, right? Okay. So it is like xi minus 1 to xi, comma, I cross yj minus 1 to yj, it's a small rectangle. Of course, it is sitting inside the big bounded rectangle. So what you have to do, diameter will exist, where I running from 1 up to n and j running from 1 up to n, and you have to take that as supremum. And diameter is finite, this is finite number, so supremum will always exist. Okay. So that I denote it as norm of the partition. So like in the single variable case, what is your norm of the partitions? You take the partitions of your interval, say x0, x1, x2, xn, where x0 is equal to a, xn is equal to b, then what you have to do, take the length of the interval, subinterval xj minus 1 to xj, that means modulus of xj minus 1 to xj, and you just take the supremum as 1 j running from 1 up to n. So you have to do the similar kind of things here. So instead of length of the interval, I am talking about the diameter here actually, which is nothing but the supremum of distance between any 2 points where x and y running over those subintervals, okay, or those set. Okay. So that is called the supremum, and supremum will always exist in this case, because I mean actually finite number of elements are there, and then that I am denoting as norm of the partitions. Okay. So now here is a note in what I have written. It varies from one book to another book. In some books, norm of P, okay, it is written as, you see, supremum of area of Rij. Okay. So instead of diameter of Rij, so they said that, okay, you just take a partitions of your square, you have to take a small subsquare which is Rij, and you take the area of this Rij and take the supremum. That is also sometimes denoted as the norm of the partitions, because at the end of the day what I want that I have to take a finer and finer partitions. That means if the norm of the partition goes to 0, now norm of the partition goes to 0 means if the area of the small subinterval goes to 0 or the diameter of the small subinterval goes to 0, in both cases norm of the partition goes to 0. So it doesn't matter. So in some books they have defined norm of the partitions as the supremum of the diameter of Rij. In some books they have defined norm of the partition is the supremum of the area of this subintervals subsquare Rij. Okay. So that is the notion of partitions of a mesh or of some grid of some size. Okay. That is called the partitions of this grid. Okay. So then what I have done, so okay, I am starting with, so now I want to define the notions of what is called the notions of Riemann-Darboux integral for functions defined on, say, bounded region square from square to scalar value, that means real value. So let R be a bounded rectangular region, that means R is of this kind of form, xy is in R2, x running from A to B, y running from C to D, and if I have a function which is bounded, I assume that it's very necessary assumption. You have to start with a bounded functions, because next slide you will see I am going to talk about the supremum and infimum, so it should exist. So unless otherwise your function is not bounded, you cannot have that kind of what is called luxury to say that the supremum and infimum exist. Okay. So what is that? So now I am starting with a bounded rectangular region. Okay. So now I am considering a partition. Now you know what is the notion of partitions. You take a partitions of the interval AB, you take a partitions of the interval CD, you put it together, then it will have a partitions of your rectangular bounded rectangular region, and each of the small rij, which is again a subsquare, okay, it looks like rij, I denote it as rij, which is nothing but xi minus 1 comma xi. So if you remember, this is actually xi minus 1 comma xi cross yj minus 1 comma yj, and that I denote it as rij. Okay, I is running from 1 up to m, j is running from 1 up to n. This is called a mesh of R. Okay. Now on each subrectangle or cell, that is, you can also say that this is a cell. Okay. So like in the case of single variable, it is a subinterval, small subinterval, partitions with small subinterval xi minus 1 to xi. Now since I am in R2, I am saying that it is subrectangle or some cell which is rij. Okay. So once I have a subrectangle or cell rij, now you define two number. One is capital suffix mij and another is small m suffix ij. So now ij stands for, I am talking about the subrectangle rij. Okay, what is that? This is nothing but a supremum of f of xy or xy running over rij. So what will happen? You have a subrectangle, you varies xy on this rij, and since my function is defined on whole square, then it is in particular defined in that subrectangle, and then you take the supremum. Now the question is whether supremum will exist or not. That is why I always assume that my function is bounded. So since I am starting with the function is bounded, so this supremum always exists, mij. And similarly, you have a small m suffix ij, which is the infimum. Again my function is bounded. How I can define the infimum? You just varies xy in your interval or cell rij and take the functional values and talk about the infimum. Again infimum will exist because my function is bounded. Okay, so now I have capital mij, I have a small mij. Now I am introduced what is called delta of a suffix ij, which is nothing but area of rij, and which is denoted as, what is that? So you have a subinterval, right? So that means I is already written. This is xi minus 1 to xi, and then yj minus 1 to yj. Okay, so this is rij. So what is the area? Area is nothing but xi minus 1 times yj minus 1, and that is exactly this one. And that I denoted as area of delta of xi, means area of or length of the interval xi minus 1 to xi, and this is length of the interval yj minus 1 to yj. So this is another notation. So I have capital mij, small mij, and area of the cell rij, where delta of xi is nothing but xi minus 1, delta of yj, that means yj minus 1. So now I have everything. So now I have a functions defined on a rectangular region. I am having a partition P whose cell rij I have already said. Okay, I have defined three things. One is capital mij, which is supremum of f over xy running over the cell rij. Then I have a small mij, which is the infimum where xy running over rij, and I have the area of this cell. Okay. Once I have these three objects, then I can define what is called upper sum, lower sum, or upper integral and lower integral. Like in the single variable case, you have done it. So what is upper sum? So upper sum, so that means I have a functions, I have a partitions, and then corresponding to function and the partitions, I will denote it the upper sum. So now this time it's a partition. So like a single variable, you have only one indices. Now this time I will have a two indices. I stands for the x-axis, that means for the interval AB. Y or j stands for the interval CD in the y-axis. So that means I have a I from 1 up to m, j from 1 up to n. Two indices. Then double sum will be there. Then you just write mij, that means the supremum, and then times area of this cell rij. Similarly, you have a lower sum, you can define, I denote it as L P of A, P is the partition, F is the functions, then again it will be the double sum, then you place instead of capital mij, I will have small mij, and then you have the area of the cell rij. Okay, so this is called upper sum and this is lower sum. What is upper integral? Upper integral, again this is the notation, this is integration over Rf upper, this is upper and this is lower. So what is that? Again, what you have to do? So you have to just, for given partitions and the functions, you have one UPF, that means the upper sum. Then what you have to do? You have to consider the infimum of all those upper sum and for the lower integral you have to consider the supremum of all those lower sum. So, that means once you have the notion of upper sum, upper W sum or lower W sum, then you can define what is called upper integral and lower integral. If I consider the upper integral, then you just consider the upper sum, because if I have a function, function is given, right. If I have a partition, then the corresponding UPF will change. Okay. If I have another partition, you have another UPF. So, that means collect all UPF as P running over, you see what is this notation pi, capital pi. So, our capital pi denotes the collection of all meshes of P of the rectangular region R. Okay. So, therefore, it says that yes. So, what you do? So, that means you have a rectangular region, you consider all partitions. Now, for each partitions and the functions you have one UPF. Okay. Now, you collect all UPF and you have to take the infimum. And similarly, what will be the lower integral? You collect all LPF, like all lower sum. So, given a functions and given a partition, you have LPF, and then you have to consider the supremum. Okay. Now, if my function is bounded, then of course upper integral or lower integral, this will exist, that means infimum and supremum exist, and with some conditions, if these things happen, then I will say that my function is Riemann Darboux integrable. I have explained in terms of tried to explain that pictures explaining upper sum and lower sum. So, what is that? So, suppose this is my, it is very difficult, but I just tried to explain. So, now what is upper sum and what is lower sum? If you remember, that means in the Legend single variable case. So, somehow if I think about as a area for, like if I have a functions from closed interval a b to r, and if I want to talk about the area. So, that means for upper sum it will give you the area of your curve and the x axis little more, okay, and whereas the lower sum it will give you the area little less. So, that means that's exactly it's going on here actually. So, that means I want to have the exact area. In that case, of course, area will not be there, it will be the volume. So, that means what will happen. So, you see, so this is little bit I am talking about the height mk, that means I am talking about the upper sum. Okay. Upper sum will just somehow it gives the area little bit more, the exact one, and this is the smaller one, that means it is little less. So, now if I take finer and finer partitions, somehow upper sum will decrease and lower sum will increase it, and at the same when non p goes to 0, and they exactly equal to the area of this kind of things or volume of this kind of things. So, that's how the kind of pictures which explain upper sum and lower sum. So, upper sum means the exact things you want, it will give you some little more, and the lower sum with whatever I want exact things, it will give little less. So, now if partition goes to 0, that means if I take more and more finer partitions, so upper sum will decrease and lower sum will increasing, at some point of time they become equal, and that will give you the exact quantity that you want. Okay, that is I exactly said. So, let f be a functions from same R subset of R2 to R be a bounded functions. The function f is said to be Riemann integrable, I said that, or Riemann Darboux integrable, or simply integrable over R if this upper integral is exactly equal to the lower integral. Okay. In this case, the common value is called the Riemann integral of f over f, and it is denoted by this. So, integral over R f, or sometimes integral over R f x y dA, or some over integration over R f of x y dx dy. So, these are the various notations I can talk about once my function is Riemann Darboux integrable. Okay. Now, since f is real valued functions of two variables, okay, as I said, so you can have the same notation or same concept you can extend in the context of more than two variable. Of course, R2 I have explained because you have a complete picture there, but instead of R2 you can extend the same notion in R3, you will have a kind of parallelepiped, and then you have to take the partition. So, same notation. So, only the variable will increase. Okay. So, but same notations you can, or same concept you can extend in the context of functions from Rn to R. Now, since I am in n is equal to 2, so I am saying that, or I am dealing with real valued functions of two variables, I am saying it is a double integral or over the region R. Okay. That means, if I have a bounded functions, if I have a rectangular bounded rectangular region, take the partitions, make a upper sum, make a lower sum, out of upper sum and out of lower sum you define upper integral and lower integral. Okay. Then you say that yes, if I have a bounded functions, a function is said to be Riemann integrable or simply integrable if the upper integral is same as the lower integral. So, that is one of the definitions that again you are familiar in the context of real single variable calculus, and also next slides I will talk about the integrability in terms of the Riemann sum. That is another way you can talk about that. Okay, one example, I just see the example. For example, if I take this what is called rectangular region, bounded rectangular region, now I am starting with the functions f, which is a constant functions. Okay, so that means f of x y is equal to k or x y running over r. Okay, k is real constant functions. Then let's see what will happen, what will give the upper sum, what will give the lower sum. Now it is straightforward to calculate that upper sum will exactly equal to k times b minus a and d minus a. And it's okay, because if you remember what is my UPF, so UPF is nothing but I think I from, if I write it here, so this is I from 1 up to, okay, go back. So let's see, I from 1 up to m and j from 1 up to n. So I from 1 up to m and j from 1 up to n. Okay, then capital Mij. What is capital Mij? Which is nothing but the supremum of f if xy running over this cell Rij, but here function is constant. So Mij here it will be exactly equal to k. And then what we will have is the delta, like that means the length of the cell. Look at here. So length of the cell, delta of Aij. What is delta of Aij? Delta of Aij is nothing but delta xi, delta yj, or in other words xi minus 1 times yj minus 1. That means area of this cell Rij. So if I, what is the area? So if I define it, this is nothing but what will happen, xi minus 1, okay, then yj minus 1. Okay. Then what will happen? This is a double sum, k will come out, and this is two indices, they are separating. So then what will happen? This is I from 1 up to n, xi minus 1, then times j from 1 up to, this is m and this is n, yj minus 1, so k times mn. Oh sorry, what is this? K times. Now what will happen, this one, this is actually you have a partitions of your interval AB, and you just take the length of the sub interval xi minus 1 to xi, that is nothing but xi minus 1, and if you sum it up, that means all term get cancelled, only the length of the interval will be remaining, that means the only the first point and the last point. So that means it will give you b minus a, and similarly this will give you what is called d minus c, and which is nothing but this one. Correct. Similarly, you can have the lower sum, which is LPF. It does not matter because function is constant, right. So capital M suffix ij or small m suffix ij, both of them in this case will be k, and k will come out from the double sum. And if you just sum those area of this cell, and if you just sum it up in both sum I and j, it will give you just length of this full square, that means which is nothing but b minus a times d minus c, and which is nothing but this one. Once I have this one, so upper sum is fixed independent of your partition, lower sum is fixed independent of your partition, which is these two values. Then upper integral, what will happen, which is the infimum, and it is all UPF are constant. So this is nothing but exactly equal to k times b minus a times d minus c, and lower integral is nothing but supremum, which is k times b minus a times d minus c. So now in both cases upper integral and lower integral are same. So therefore my function is Riemann-Darboux integrable, and what is the value? Value of the upper integral and lower integral, both are same. So this is value of the integral. Okay. So this is very simple functions. So you can explicitly calculate just using the definitions, and you have the examples of one Riemann-Darboux integrable functions. However, if I have another example which is non-integrable functions, and what is that? Again I am just having the same bounded rectangular region, that means x is running between a to b and y is running between c to d, where a is less than b and c is less than d. Now this time I am considering a functions fxy which is taking value where xy is running over r, but x is a rational number, y is a rational number, and f of xy is 0 otherwise. This kind of functions you know, right? So one single variable case, f of x is equal to 1 if x is rational, 0 if x is irrational, or either way around. Okay. Similarly, what I am doing, I have a rectangle. Okay. So in rectangle I am defining, so of course you have a point x comma y, right? So either xy could be rational, could be irrational, x could be rational, irrational, y could be rational, irrational. So I am saying that if both x and y are coming from Q, it is taking the value 1 and rest it is 0. If I have that kind of functions, then let us see what will be the upper sum and what will be the lower sum. Again it is a what kind of function, its value is actually constant, either 1 or 0, it taking either two values, right. So therefore if I take this again, I from 1 up to m and j from 1 up to n, and then mij times your area of this aj, I think this aj, area of this cell Rij, then what will happen Mij? So Mij has what will, so it is taking either value 0 and 1. So that means if it takes value 1, so its supremum will be always 1. So that means this should be 1 actually. So it will 1. So that will what, now if I take the sum over I and sum over j, and it is the area of your cell, then what will give you? This is give you the whole area of the rectangle, which is nothing but b minus a times d minus c. Correct? Because if I take any Rij, which is the small cell, it contains both rational and irrational points. So that means at least you have xy which is rational, and at least you have 1x, 1y, either x, one of them is not rational. So if one of them is not rational, that means and its 1 point value is 1 is there. So that means Mij is the supremum, so therefore it is taking the value 1, and if I take the infimum Mij, small Mij, it will be 0. So therefore in the lower sum it will be 0. So that means even if I have a b minus c or d minus c, it will not contribute. So because small Mij, infimum will be there, because it is taking the value 0 at least 1 point, because you have a cell Rij which contains both rational point and irrational point, and rational and irrational both are dense. So that means you have at least 1 point which both components are rational, at least 1 point whose one of the component is not rational. So either so that means taking 1 value as well as it is taking the 0 value. So therefore it is, the lower sum will be 0, upper sum will be length of the square. So now this is independent of your partition, this is also independent of your partitions. Now you perform the upper integral, which is nothing but infimum of UPF, which is constant, that means it is exactly the value b minus a times d minus c. Similarly you have a lower integral, which is nothing but supremum of LPF, which is again taking the value 0. But in that case what will happen? My function is Riemann-Darboux integrable, upper integral should be exactly equal to lower integral, but this time this value is different. So therefore my function is not Riemann-Darboux integral, or in other words double integral r f x y dA does not exist. I think I should stop here. So this is actually one way I have defined the concept of Riemann-Darboux integral if I have a bounded functions, and if I have a function defined on a bounded rectangular region. So what I have done, I have just taking a partitions of my interval, if so starting with a bounded rectangular region, say which is of the form a to b cross c to d, I am taking a partitions of ab, take a partition of cd, combine it, I am getting a partitions of my rectangle ab cross cd. Then I am associating a small cell Rij, I have defined the notion of partitions, and then I have defined what is called upper sum, lower sum. Associated with upper sum and lower sum, I have defined upper integral and lower integral. Then I said my function is Riemann-Darboux integrable if upper integral is same as lower integral. And then I have discussed an example. In some example, some function, constant functions, easily you can calculate. My function is Riemann integrable and its value is whatever. And then I have discussed another function which is a very bad function. So for that functions I have checked that, or I have discussed that upper integral and lower integral exist, but they are having the different values. So therefore my function is not Riemann-Darboux integrable. In my next lecture I will talk about, and in fact I define the same concept, the Riemann-Darboux integrable, in terms of what is called Riemann sum. That is also you are familiar with in the context of single variable. I think I should stop here. Thank you.